Okay, let's continue our discussion on symmetries. And today we begin by asking what are the questions that we ask in a quantum theory. So, the things that we ask are what is the probability amplitude of one state evolving into another state, okay, or what is the probability amplitude of a state alpha, okay, that we find it in some state beta. Okay. So, these are the kind of things that we are interested in when we are working in a quantum theory. Now, how are we going to construct states alpha and states beta? Okay. So, let us list down the things that we have got. We are given the ground state of the theory. For the free case, we denote the ground state by this, we also call it vacuum. Okay. And in general, if the theory is interacting, we represent the ground state by ket omega. So, that is a ground state. Okay. How do you create other states? Well, you do so by acting on the ground state by operators, and the operators that you have.
Auto charging will start soon. System initializing. Please do not move the robot.
So, the states that you create in quantum theory is by acting with operators. And what operators do you have? You have the field operators and the operators called which you obtain by obtain from the momentum densities. Okay. So, if you wish, I can put a hat for a while. Okay. So, these are the operators that you have in your theory. So, everything is going to be constructed out of these objects. Okay. So, you act with phi's and pi's on the vacuum to create different states. Okay. So, all that we want can be formulated in terms of these operators and these states. Okay. So, how about our discussion on symmetry that we had? What does that imply for the states that we construct? See, one consequence that we found from symmetry was the existence of Noether charges, okay, conserved currents and Noether charges. Okay. That is one thing we found, but we can expect that those symmetries, okay, under which the action is going to remain unchanged, or even discrete action is going to remain unchanged, they will also affect, or they will have consequences on these objects, on these matrix elements, okay, and that is what we plan to explore in this video. So, for example, if you are looking at translations, okay, if you are looking at translation symmetry where you take the field operator phi, okay, and you transform it to the operator phi tilde of x. Remember, we have now we are talking about quantum theory. Okay, now we are not looking at field as a classical field, but rather as a field operator. Okay, where phi tilde of x is phi of x plus a. Okay, if this leaves the action invariant, okay, then we expect that if you are looking at the probability amplitude that this state alpha is in state beta, okay, this will reflect upon transformation this fact. Okay. So, if alpha goes to some other state under this transformation, beta goes to some other state in that under that transformation, the inner product of that let me call it alpha prime. So, alpha goes to alpha prime under this translation, and beta goes to beta prime under that. So, we expect that the probability amplitudes of finding alpha in beta and alpha prime in beta prime, they would be the same. Okay. So, that is what we expect. We can put a modulus here, okay, because it is a statement about probability, but the amplitudes may change by a phase. Okay. So, where I have said that under the transformation ket alpha goes to ket alpha prime, whatever the transformation is, for example, translation in this case, beta goes to beta prime, and we expect this kind of a relation. Okay. Now, when you go from alpha, I mean you are taken from alpha to alpha prime by some operator u. Okay, so let us call it u. So, u is the one which takes you from ket alpha to ket alpha prime. So, that is the operator which does this, okay, meaning the operator u is the one which is implementing the transformation that is happening due to symmetry operation. Okay. Now, the requirement that these amplitudes, the modulus of these amplitudes that remain unchanged has a bearing on what u can be, and it is a theorem by Wigner. It is called Wigner's theorem. Okay. That either u will be an unitary operator So, u would be either a unitary and linear operator, or u will be, or u is an anti-unitary and anti-linear operator. Okay. So, these are the only two possibilities for the operator u, and I am here not only talking about the translations, I am talking about all symmetry transformations that we can have. Okay. Now, I will in this course only talk about the unitary operators. Okay. I will not discuss anti-unitary, and anti-unitary operators arise when you are looking at time inversion. Okay. So, that is something we are not going to discuss, and the proof of this theorem you can find for example, in Weinberg volume 1. Okay, and you can also find discussion on anti-unitary operators there. Okay. So, for us u will be always unitary because we are not going to consider time inversion. Okay. Okay, so let us look at a state alpha in our Hilbert space. Okay. And let us say that we do a transformation by so the transformation operator is T1. Okay, so that is the transformation we are doing, and in the Hilbert space this transformation is done by the unitary operator T1. Okay, and if we look at look at another transformation T2 which acts on this. So, I am doing one transformation after the other. So, first I do T1 and then the T2, then this state. So, let me write it like this. So, alpha goes to u T1 of alpha, and then this state, if I do further transformation, it will go to this one u T2. Okay. But we could have done this in one go. So, instead of doing first T1 and then T2, I could have started from alpha and done T1 T2. Okay. So, T1 on the right means first this is the operation. So, this product I can do in one go, and then it should give me the unitary operator corresponding to this transformation. Okay. which means that I should get u of T1, u of T2, this acting on alpha, this one same as okay. But there could be a phase, because if there is a phase, the probability amplitudes will not change, but I am not going to include the phases here, and a discussion on that you can find in Weinberg volume 1, for example. Okay. So, this is what we get, and which means that these unitary matrices should satisfy the following property, that u T2 u T1 is equal to u T1. I should have written it other way. So, let me do it. Okay, and that is what the property of a representation is. So, this is saying that if you are looking at these matrices, these operators T1, T2, then they will form a group, as we have seen, and the group will have property that T1 I mean, so this is the group multiplication for the representation generated by the unitary matrices. Okay. So, this is one thing I wanted to tell. So, the U furnishes a representation of the symmetry group. Of transformations whose elements are T1, T2 and T3. Okay. Okay, that's fine. Now, I will try to put these things in a context that is familiar to us, which we already knew. Okay, and then after we have talked about that familiar setting in which we are already aware of these results, I will move on to a general discussion. Okay. So, for that what I do is I start looking at quantum theory in the Heisenberg picture. Okay. So, here as you know that the operators evolve with time and the states are independent of time. So, if you are looking at an operator O, then its time evolution is given by this. Okay. For now I am putting IH bar, but later I will drop. So, this equation you are familiar with. Okay. It is the Hamiltonian of the system, and you are taking a commutator with the operator O. Okay. And the states do not change, they do not evolve with time. So, if you have some state psi or alpha whatever, then that does not evolve with time. Okay, because the entire time evolution time dependence has been transferred to the operators away from the states. Okay, so that is an equation we know. So, what is the solution of this equation? This is this differential equation. The solution is this: e to the I over h bar h t minus t 0 okay. We can immediately verify that this is indeed true, that this is a solution. So, let us check that. So, if you calculate d over dt, okay, this is anyway a constant, so it does not matter. This one, when I take the derivative, it will give me I over h bar times h, but that h I can put this side or that side, does not matter, because it will commute, because this object is made up of only h. Okay. So, I can write it as I over h bar times h okay, times the same thing again. Then when I the derivative acts on this one, it again produces the same thing with a minus sign. So, you get minus I over h bar, and this entire thing is again h O t, sorry, this entire thing is again O of t, and the derivative has pulled out an h, which will be on the right side. Okay. And this is what we have. Okay, so if you take the minus sign iota and h bar that side, you see this is exactly what you get, your differential equation. So, this is indeed a solution to our equation here. Okay. So, this this equation here, let me write it slightly differently, this one. Let me write it as minus I h bar, okay, O at time t plus delta t minus O at time t, okay, Z okay. So, you see that your operator evolves from O of t to O of t plus delta of t, and the difference, okay, that difference between the difference is given by this this commutator on the right hand side. Okay. So, we say that h is the generator of time translation. See, you have translated in time, you were at time t, then the operator evolved to time delta t, and this translation from t to delta t has been carried out by the operator h. Okay. So, we say that h is the generator of time translation. Okay. I will drop h bar and put I there on the right hand side, which makes it the following, a little bit cleaner. So, I multiply plus I from on both sides, I get this. Okay. So, you see, this is the infinitesimal version of this statement, right. Here you are starting at time t 0, and these two unitary operators take you to time t. Okay. So, you evolve from time t equal to 0 through this unitary operators and reach at time t, and this is the infinitesimal version of it. It is saying you go from time t to time t plus delta t through generator h. Okay. So, these are two same statements, one is infinitesimal version of the other one. Okay. So, let us take that operator O to be phi. So, let us take the operator to be phi, okay, and I want to write this this statement for phi. So, phi of x t I can write as e to the I h, I am dropping the h bar now, t minus t naught, phi of x t naught. So, I am starting from time t naught and evolving to time t, minus I h t minus t naught. Okay. So, this is what you get from here, and clearly if you find the commutation relation, you will get phi of I mean this relation where O gets replaced by phi. Okay. So, this is good, this is for the time translation. Then you realize that when we were calculating the conserved charges, Hamiltonian was you got Hamiltonian when we were looking at time translations, but you got 4 generators corresponding to space time translations, the p mu's, okay, which was h and p. Okay. So, we have 4 generators. So, if I were to look at not just time translation from T naught to T, but look at space time translation. So, I start from x naught and T naught and evolve to x t. I should expect that I will get something of this form, not something, but I should expect the following. Okay. So, p mu, and then you get x minus x naught mu, and here I should get minus I p mu x minus x 0 mu. That is our expectation, okay, purely from relativistic ground, because I know that p mu is a 4 vector and I know what one component is doing. So, I can almost guess what other components should do. So, let us look at the infinitesimal version of our expectation. So, what I have to do is just take x minus x naught to be infinitesimal and expand this, and let us see what we get. So, I get phi of I can work with. So, x is x is this. So, you have from looking at the above thing, you have e to the I p dot epsilon is the same thing which I wrote, but now x minus x naught I have written epsilon, and instead of mu's I have put a dot, and you have phi x naught, where x naught is this e to the minus I p dot epsilon. Okay. Now, I expand, so I get 1 minus I p dot epsilon phi x naught 1, sorry, here it will be a plus, minus I p dot epsilon. Okay, so, this is phi of x naught plus I, and you get the commutator. And order epsilon square terms, okay, which we will not worry about. Okay. So, we say that phi x minus phi x naught, that is the translation that has happened, is generated by the operator p mu. Okay. So, p mu, this momentum operator is the generator of space time translations. Okay. So, we say that p mu generates space time translations, or it is the generator of space time translations. Okay. Now, of course, if you put mu equal to, so you put epsilon 0 to be non-zero and all others epsilon to be 0, okay, then you get the p 0, which is Hamiltonian, and you recover this equation, this one. Okay. And similarly, now we can put epsilon not to be 0 and look only at space translations, then you will get the following. So, if you are looking at epsilon not to be 0 and all other epsilons to be 0 non-zero, okay. Okay. Then you get phi of x naught is fixed, okay, and here I have x1 plus epsilon, I can put epsilon 1, x2 plus epsilon 2, x3 plus epsilon 3, okay, minus, so time is again kept at the same value. Okay. What that would be? That would be, so I have just taken to the left, taken the difference, and I have I p phi x naught, and so I can put a dot here. Okay. this is correct except for a sign. So, here you have p mu epsilon mu. So, your p is this, your epsilon is okay. So, p dot epsilon will have a negative sign for the space part. So, that is the minus sign here. Okay. So, if you look at this, this is the difference, and if you divide by the change, you get the following. You get divergence of phi dot epsilon. Okay, yeah, I am doing a Taylor expansion here. It's equal to minus I p phi x naught dot epsilon, and which tells you that p phi x naught, this commutator minus I is gradient of phi. Okay. So, you see that this the p generates space translation. So, we say that this momentum generates space translations. Now, this was based on guesswork that the transformation of the field under space time translation would be of this form, okay, which was a good guess, but now we are going to prove it. Okay. So, we will appeal to the Northwest theorem, which we have used and which we have studied. So, recall that for infinitesimal transformations, for whatever symmetry you are looking at, your transformed field we wrote like this. So, epsilon is the small parameter and the change we wrote as this. Okay. So, this is the part which is the change in the field. Okay. And we were considering these actions for which we can write down an explicit expression. Okay, we were looking at the theories for which we have only single time derivative, single derivatives of fields. Okay, and we had found that the conserved current J mu we can write in the following manner. Okay, the Lagrangian density, and you have to take the derivative with respect to del mu phi a, and I should sum over all the fields. Okay, and this has psi a, and there was a minus k mu term. Okay, and q, the charge I get by looking at integral d cube x of j 0, okay, which is the following, del phi dot. So, I put mu equal to 0, so that becomes a del phi dot psi a minus k 0. Okay, that is the conserved charge q corresponding to this symmetry. Okay. Now, recall that del L over del phi dot a is this, is pi a of x, okay, where pi is the momentum density, which says that I can write q as d cube x summation over a pi a psi a minus k 0. Okay. Okay, good. And my experience shows that I should be constructing quantities like this. So, I take the conserved charge and look at a commutation relation with phi. Okay. So, that is what I am going to do. So, I will take q, okay, and look at the commutation relation with respect to phi. Okay, let me write it like this. So, q That's the commutation relation I want to make. But then I remember that I know, see the Q is made out of size and pies and fields. Okay. So, I have to use commutation relations, but I know commutation relations at equal times. Okay. So, it is useful to have Q at time t here, because here I am writing at time t, and it does not matter because Q is time independent, right. We have shown that dq or dt. So, you can choose whatever time you like, and this is useful because then I can use equal time commutation relations. Okay. So, I have integral d cube x prime. So, I use a dummy variable here, summation over a pi a of t x prime. So, this time is same as here. Then I have psi a of t x and minus k 0 of t x prime prime. Okay. So, that is what I get. Okay. No, I forgot to make the commutator. Sorry, just a second. So, so I have to take a commutator phi x t. Here was a prime. Okay, there was a prime here, and you have this commutator, and you have this additional term with k naught. So, you have minus k 0 and t x prime phi x t. You have one more commutator here. So, the summation is for this one, that is the commutator, and this closes here. Okay. So, that is what we have in general. But if I am looking at transformations such as space translations, okay, rotations, and other internal symmetries. Okay, in those cases, k 0 will be 0, as you can verify. Okay, and the psi a, which is the change in the field, will not involve pies. Okay, so psi a will be independent of pies. Okay. Okay. So, in these cases, the result that I am going to prove, I am trying to prove, becomes easier, because then this term is not there. Okay. And here I do not have to worry that psi may have pies, and okay, I just have one commutation relation between pi and this phi, and that makes our life easy. Okay. But the result which we are going to derive is true in general, but we are going to work in this simplified context, this easier context. Okay. Okay. So, what do I get? So, I will leave this term out, okay, because of I am saying I am looking at these ones, and then all I have to do is use this commutation, work out this commutation relation. So, the psi, because I am saying it is made up of only phi's, that one will go out and sit on the right, and I will have a commutation relation between pi and phi. Okay, and that, you know, it gives a delta cube, and that I can integrate easily. So, let me do that. Okay. So, q of t, what did I write here? I should have written phi of a, okay. Phi of a, okay. And here you can make the variable, the dummy variable as b. It will be less error prone then. Okay. So, good. So, we have qt phi a t x commutator. I am just writing what I had in the previous slide, d cube x prime, and then I have summation over pi of b t x prime, and then you have phi a t x, and as I said, the psi will come out. Okay, because this will commute with the phi. We have assumed the psi depends on phi only. Okay, and this one I use the commutation relation, and the commutation relation is that this object is the following: d cube x prime minus I delta cube x minus x prime, okay, times psi b of t x prime. Okay, I am missing a prime every time. And this gives you, when you do the integral over x prime, it gives you minus I psi, there is a delta a b I should put, because this is b, this is a, so I have a delta a b. So, you have psi a t of t and x. Okay. So, this is the general relation that I have proved, and you see the change in phi was psi, right. The change in phi was psi, of course, there is an epsilon, but the coefficient of epsilon is psi, and we see that psi, or the change in field, is being generated by the generator q, or the charge q. Okay, so, q is called the generator of symmetry transformations. Okay, and this is exactly what you have seen for time and space translations. Okay, even though the proof I have given does not apply for time translations, but the result is general, as you see that this result coincides with what you have here, this one. Okay, so this is a nice result that we have proved. I will stop the video here, and we will continue discussion in the next video.